but you will be getting the notes. Right, can anyone remind me what you did in yesterday's lesson? Force fields. What is a force field? Or where to? What were the different types of force fields we spoke about? Magnetic, gravitational, and electric force field. Those are three types. There may be more. Can you remember what a force field was? Who can? Okay, so if we're talking about a gravitational force field, it's an area in space, an area, where an object with mass experiences a gravitational force. If it was an electric force field, what type of particle? Area in space where a charged particle experiences a what type of force? Coulombic force. Okay, we then also had a look at the shape of some of these force fields. For example, we said if we had a positive particle, what was the shape of that field around it? Each field has got its own shape. It consisted of lines that were running out of it or into it. Okay. Now, how long have I taken to draw this force field? Half a minute, 30 seconds. Did I rush it? No. Is this a difficult question? Would you like to get a question like that in your tests and exams? Yes. This is primary school stuff, isn't it? Now it will come up in matric exams. Draw the shape of the electric field around whatever. They mark it quite strictly, however, because it is so easy. You shouldn't have stuff this easy in a science paper. So what are the things that they look for? First of all, I'll show you one where people rush it and get marks taken off. Right, they draw the positive particle and then they draw the lines. Okay, what's wrong with that? There are two mistakes there that that person's going to lose marks for. The two mistakes actually are in the same place. Well, first of all, let's take that area there. What is the problem there? Those two lines come from the same point. They're touching. You agree? Now, the field lines, are they really there? No. But what do they indicate to us? The direction that what would experience a force? A what type of particle? What type of charge? So if I had to put a positive charge on that line, it would move in that direction. If I had a positive charge on that line, it would move in that direction. If I had to put a positive charge there where I'm putting this blue dot there, which is where those two lines touch, which direction would that positive particle move? Two directions? Can't be. Okay, so for that reason, field lines never ever touch. If they touch, you lose a mark straight away. Also, field lines begin and end at 90 degrees to the surface. Is that 90 degrees there? No. Okay. Now, are each of those 90 degrees? No. Did I use a protractor? No. But you can see they more or less are perpendicular to the surface that they come out of. Do you agree? So I'm not saying go and use a ruler and a protractor and take 10 minutes to do it. 30 seconds is fine, but draw it carefully. Don't draw it like this, because this person would get 3 out of 3. This person would only get 1 out of 3. Because there are two errors. The one error is field lines are touching, and the other error is that the field line is not starting perpendicular to the surface that it originates from. Right, all with me on that? So please be careful about that. There's a lot of pupils lose a lot of marks in matric exams for that. Not only matric exams, all exams. Right, now just to carry on with our revision, if I had to go and put a little positive particle there, where would that positive particle experience a force? With the field or against the field? Positive particles experience a force with the field, so that would be that way. However, if I had to put a negative particle into that field, if I had to put a negative particle there, which direction would that negative particle experience a force? Against the field. So negative particles experience a force against the field. Positive particles experience a force, that is an F force, and therefore it will probably move in that direction if there's nothing holding it back. And that is a force there. It will probably move in that direction if there's nothing holding it back. All happy? Good. If I had to draw a negative force field, or force field around a negative particle, how did we say that would look? They would be exactly the same shape, but they would all move inwards. Once again, am I using a protractor? But it is relatively correct. Right. Now, if I had to go and put a positive particle somewhere in this field over here, where do you think it would experience a force? If I'd drawn a line there, that line would have been running that way. Do you agree? So would it run outwards or inwards? Outwards, it would experience a force that way. No. They go with the lines, okay? The lines are running in because it is a negative force, a particle causing that field. So that's the direction that it would experience a force. All happy? There we go. If, however, we put a negative particle, which way would that negative particle experience a field? Experience a force against the field. Right. All happy with that? Then yesterday, we also drew a situation where you had a positive particle next to a negative particle. And we said, what does that field look like? Anyone remember? It basically looks a bit like these two fields combined. The one runs out straight in, that's no problem. Would have gone out, would have gone straight in. This one would have left at about 45 degrees, but now it gets pulled in there. Happy? 45 degrees, that's that one. That's the equivalent of that one and that one. You agree? This one would have left at 90 degrees. It's going to get pulled around and approaches at 90 degrees. That's right. All happy with that? Maybe this one's a little, so we'll put the top one on. Okay, happy. Right, what would happen in the following situation? How's that force pattern going to look now, the field, force field pattern? They all flow out, don't they? So this one and this one are going to cancel each other. You're not going to get anything there. These two are going to repel. You agree? Same with these two that are coming out at 45 degrees. Happy with that? Right, and if I were to do 2 negatives, what would that look like? Exactly the same. These two that would be going inwards would cancel each other out. Okay, everything else would look exactly the same as the other one, but don't make life difficult for yourself. Okay. One line looks a bit dodgy. Right, happy? Okay. What would happen if I gave you 2 parallel plates like that? Okay, let's draw them in another color. Don't get confused. What would happen if I gave you two parallel plates that were connected to a battery of cells? Have a look at that and tell me what you think is going to happen there. What? Will those 2 plates attract each other? Let's say they're not allowed to. Let's say they're clamped apart from each other. Sparks. It's just a battery. A little 1.5 volt battery. If it was a very strong battery, yes, you would get sparks jumping across, but let's say it's just a good old pen-light battery. What would happen to this plate? What charge would it pick up? We know that that's the positive terminal of the battery, am I right? So this plate would be positively charged. And we know that this is the negative terminal of the battery. So this plate would be negatively charged. Would current flow in which direction? I disagree. What is the first requirement for a current to flow? A complete circuit of conductors. Do I have a complete circuit in this area? No, I've got a big gap here. There's air. Okay? So, no. But what happens is this plate becomes positive, this plate becomes negative. If I had to connect them, yes, then current would flow. But as it is at the moment, current can't flow. But it doesn't mean that an electric field can't be set up. Now, how does the electric field look in this space here? So you're saying lines running from positive to negative, like that. Okay, that's what they look like, lines running from positive to negative. In fact, some textbooks even show them coming right through, going right through. They don't stop. We're more interested in the lines in between the plates than on either side of the plates. On the ends, the lines curve a bit. Like that. So that's the shape of your electric force field, your electric field, when you've got 2 parallel plates. That's the shape between 2 parallel plates. And it's a very important shape. We'll talk about why it's an important shape in a moment, or an important setup. Let's go back to this one over here. Where is the field strongest? Closest. Common sense tells you it's closest. That's where. Okay, let's go here. Where's the field strongest? Closest to the one, closest to the other, in the middle. Let's go to another type of thing. If I give you grid lines on a map, where is the gradient steepest? where the lines are closest together. Where is the field strongest? Where the lines are closest together. Okay. Now if we take this diagram here, if I said that point there, where I'm pointing there, or that point there, A or B, where are the lines closer? B. Yeah, the lines are about 4 or 5 centimeters apart. Yeah, they're about 10 centimeters apart. You agree? So over here we have a weak field. The field gets stronger as we get closer because the lines are getting closer. So the closer the lines, the stronger the field. Okay. So what can you tell me about the field here? Weak. Okay. Almost no field. But over there, you've got a strong field. Now, where's the field strongest here? What can you tell me about the field? There, 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 there. It's the same everywhere. So yeah, for the first time, you have what we would call a uniform or constant. A uniform electric field. That's important. Where is the only places between those plates where the field is not uniform? On the edges where the lines curve. But otherwise the lines are parallel to each other, so that means they're evenly spaced. And you should draw them approximately evenly spaced. Once again, you don't have to take a ruler and measure. Okay? But make sure you draw them so that you can see, yes, to the naked eye they look parallel and they look as if they are evenly spaced. That means you've got a uniform field between these two plates here in this middle area. On the edges, the field is not uniform. Uniform means the field is the same anywhere. Okay. Now, what would happen if I put a positive particle here? Where would it experience the stronger force? Near the positive plate or near the negative plate or in the middle? Why? Okay, hold on. Who said near the positive plate? Hands up. Why do you say it will experience the greater force near the positive plate? Positive repels positive. That's why it experiences the greatest force near the positive plate. Who said near the negative plate? Why? Because negative attracts positive. So what is actually happening? Are you having positive repelling the positive or negative attracting the positive? As the one gets weaker, because it's moving away from the positive plate, so the repulsion gets weaker, it's moving closer to the negative plate, so the attraction gets stronger. How do you start working that one out? That's why I said to you yesterday, how do you judge which way the particle is going to be forced? Positive particles move with the field. Negative particles move against the field. We stop talking about repulsion and attraction. Okay? It gets a bit tricky. I'm not saying you must forget about repulsion and attraction, but when you're talking about electric fields, don't think about that. You just say, if I'm putting a positive particle in there, it experiences a force with the field. And that force will be a uniform force because the field is the same everywhere. However, if we were to put that particle there, what would happen to it? It would be forced with the field or against the field? With the field. Now, tell me what happens to the force as we get closer to this particle. Why is it getting stronger? Because the lines are getting closer, the field's getting stronger, so therefore the force is going to get stronger. Understand? Over here, tell me about this force here. It's going to be a constant force all the way through. Tell me about the movement of that particle. Constant velocity. What does a constant net force cause an object to do? Accelerate. This particle will accelerate. Uniform acceleration. Its acceleration will stay the same, but its speed will get more and more and more. What will this particle do? Its acceleration will accelerate. Okay? So this gets quite complex. This is a nice simple way. That's why this is important. They use it quite a lot in science. Right, all happy with that? Okay? What would happen if I had to put a negative particle, let's say an electron, over there? It would move against the field. that way. Experience a force towards the left. Why is it being forced towards the left? Is it that this plate is repelling it? Is it that that plate is retracting it? No. It's a negative particle. It will therefore move against the field. That's the way you reason from now on. All happy? All understand it? Good. One more. A hollow metal egg. Okay, a hollow metal egg, and I charge it negatively. Where's the charge going to go? If I charge it negatively, is the charge going to be on the inside or on the outside or both? The charge will be on the outside. What do you notice about how I've drawn the charge? Where is the charge more concentrated? At the point, at the sharp point. So electric charge, I don't know why, it tends to collect on sharp points. When you've got a flat surface, it's quite spread out. But okay, maybe I should have drawn it a little bit more concentrated over there, because that's a bit of a point, isn't it? Okay, so let's put a few extras in there. Maybe let's take a few of these out over here. Right. Yeah. And put a few extra in over here on the corner. But certainly on the sharpest point, there, get a lot of negative charge collecting. Then when it straightens out, the charge spreads out. On another point, it collects a bit, then it spreads out, collects a bit on that point, and then it spreads out over there. All happy, all understand. And you'll notice that the charge is on the outside. Why? Because the outside gives the charge more space. You bring it to the inside surface, it's more cramped. So it always goes to the outside surface. Now what was if this was a car, and you were sitting in this car, okay, there you are, sitting in the car. Would you get shocked? Let's say lightning struck that car, it was all charged. There is no contact with the ground, no. You're on tires. Electricity doesn't flow through tires, so it's a small lightning bolt. Your car, when an electric wire falls down onto your car's roof and charges your car negatively, would you be shocked? No, you'd be quite safe within that car. The problem with lightning is that often there's so much heat generated that your car explodes, petrol catches alight. But generally speaking, you won't be shocked, because the electricity is on the outside of your car. If you go and touch it, if someone comes from outside and tries to open the door to help you, they will be fried. But you will be okay sitting inside that car. Okay. Can anyone tell me why buildings like church buildings, these old church buildings, they always had a spire, didn't they? Can anyone tell me why they had this long, sharp point? What do you think would collect on that long, sharp point? What? Where does electricity collect? On sharp points. Okay, so yeah, you're going to have a stack of electricity on the top of that steeple, on the spire. What's that going to attract? Lightning. Was it a wise move? Yes, it was a wise move. The reason being, all buildings attract charge. Buildings like this, your houses, attract charge because the wind blows over them and either takes electrons off or adds electrons to the sheeting and so forth, to the roof sheets. So a house, a building collects electricity, electric charge. And that electric charge can attract lightning bolts, okay, which make it dangerous. especially churches which had these big expanses of roof, so they could pick up a lot of charge. Now charge collects on sharp points. So they would deliberately build a sharp point on buildings. Tall buildings still have that. If you go to Cape Town, all the tall buildings have got a metal spike up in the roof. And that metal spike, the electricity collects there, and it will dissipate from there. What does dissipate mean? It will be taken away by the wind, by the water molecules in the air and so forth, because they're trying to repel each other. So every time they get a chance, they jump off. And you'll find that the electricity disappears. It doesn't stay there. So it collects there and it disappears. So this is actually a way of getting rid of the electricity. This building becomes neutral because this is a spot where the electricity leaks away. Okay? Whereas it wouldn't leak away from the roof for some reason or other. But where it's concentrated and it's repelling each other, it will leak away. And this is one way of making sure that buildings don't pick up a charge and therefore don't attract lightning quite so easily. Okay, does that explain that? Right, I think we've covered everything in terms of what electric fields look like, how they interact. How would the field lines on this field over here work? Which way would they run? Inwards, outwards? What field is it, positive or negative? What happens with the negative? Inward. So there would be a lot of lines over here. Try and draw them, coming in. Okay, fewer lines there, few more there. Try and draw them at 90 degrees to the surface. Few more there, and then a few over here. Right, that would be your field lines around there. Right, how much time do we have? 10 minutes. Let's just have a look at a few things. Let me just give you some notes. I think we've covered everything here. Just a few notes on electric field lines. The lines flow out from out from positive, like that. Don't write them down. I'll give it to you. It's all in your notes. You'll get it. And into negative. Out from positive, into negative. Lines never cross or touch. I had told you that. Why? Because that would mean that a charged particle placed at that point would then have to move in two directions at the same time, and that's not possible. So they never cross or touch. Lines begin and end perpendicular to the surface. Draw that as best as possible. The denser the lines, in other words, the more close they are together, the stronger the field at that point. No field inside a hollow conductor. Notice I haven't drawn any field lines inside, only on the outside. A uniform field exists between two oppositely charged parallel plates. Like this, you have a uniform field, but you don't get a uniform field on the edges. There the field is a bit distorted. Okay, and then just an NB at the bottom of that page. Always draw your electric fields neatly and accurately. Right, happy with that? Okay, so I need to give you 3 pages of notes on that. You do have all the notes on Coulomb's law of electrostatics and all of that I have given you. Right, I'll make you those 3 pages of notes in a moment. What I'd like to look at now is something called electric field strength. Just how strong is this field? Is there a formula for calculating it? We know what an electric field is, but what is the strength of the electric field? So that's the heading I'm going to put up here. Right, your formula for electric field strength. And here it becomes a bit confusing again. What does E stand for? Energy, usually. Now it stands for electric field strength. So you've got to keep your head about you, okay? E stands for electric field strength is equal to F over Q. Sometimes it's a capital Q, sometimes it's a little q. What does F stand for? And what is force always measured in? And Q, charge in coulombs. Can anyone therefore tell me what E is measured in? What? Have a look. What's that and that? Newton. Why you say Newton coulombs? Per coulomb. Okay, you're dividing, so it's per. If they were multiplied, it would then just be Newton coulombs. If you divide, it's newtons per coulomb. So it's newtons per coulomb, newtons dot coulomb minus 1. Right, let me give you an example. No, I'm going to give it to you. Just do this in rough. Right, let me read that. A 2 microcoulomb charge experiences a force of 1.5 times 10 to the minus 3 newtons. Calculate the field strength. While you're doing that, I'm going to go and make your copies. Let's just mark that. Would you give me the formula, please, Nikita? F over Q, can you tell me what each of those values are? F is? Q is? Right, and that's going to give you an answer of 7,5? What? Is that all? Is electric field strength a vector or a scalar? How do you know it's a vector? Have a look at it. Certainly seems to have direction, so I would guess that it's a vector. Look at the formula. What is force, vector or scalar? So we give it a negative value. Do you agree? Have I taught you that trick yet? If you want to decide whether something is a vector or a scalar, you go to the formula. And for anything in the formula which is a vector, you give it a negative value. And for anything which is a scalar, you give it a positive value. So is force a vector or a scalar? Vector. Charge? Charge is a scalar. What is negative divided by positive? Negative. So therefore electric field strength is a vector. So you need to give a direction. Always from, you don't know where the field's running. I haven't given you enough information, so you simply say from positive to negative. Yes. Charge is positive, but remember the other day I said charge could be labeled pink and purple if you wanted to. Those are just ways that we label it. It doesn't mean that it moves in the positive direction or negative direction. Okay, all happy with that? Your notes are busy being photocopied at the moment. I couldn't get them photocopied quickly, so I will get